Hi. Hi. Welcome to Unacademy. Welcome to Unacademy. Unacademy is the India's largest online learning platform. So it is going to providing the facility for GATE and engineering service students. A better coaching they are providing. About myself, I have total 16 years of experience. So far I mentored more than 60,000 students for their GATE examination. At present I am pursuing PhD from JNTU Kakinada and my specialization is in VLSI domain. See, this lab app is in your mobile, it's okay, otherwise install that. Just go to Play Store and type Unacademy on that and then click on this install button. It will install the Unacademy learning app on your device. Now once you open that, there you get a what are the different courses available and who are the top educators handling those courses. You will get that information. You will get that information. And now just we check who are the top educators available here. See, here are some top educators: Tiwari sir, Ankit Goyal sir, Jaspal Singh sir and Jain sir. Okay, and here few more top educators. Now I'm happy to announce that new batches are going to be started from today for GATE 2022 and for GATE 2023 aspirants. There is a SN batch for GATE 2023. This is for electrical engineering department. Here are the top faculty who are handling the GATE subjects here. And it is started from 1st of February. It is going to start today itself. And again SN batch for GATE 2023. This time it is for electronics and communication engineering. Here are the top faculty who are handling the GATE subjects here. This batch is going to start from 1st of February. Next, there is a Evolve batch. This is for GATE 2022. This is for electrical engineering. Okay, here are the top educators who are handling the subjects in that batch. Now, this is also going to start from today itself, 1st of February. And don't forget to use my code VRAO10 during subscription to get 10% discount. And again, there is a Evolve batch for GATE 2022 in electronics and communication engineering department. Okay, and this batch also going to start from 1st of February 2021. Here are the top faculty handling the classes for this batch. And For in civil engineering point of view, there is a batch C batch. This is, and it is also a eval batch for GATE 2022. It is already, it was started on 25th of January. Okay, don't forget to use my code during subscription VRAW10 to get 10% discount. And here is the SN batch for GATE 2023 civil engineering. Okay, here are the top educators handling the subjects in that batch. And next, again for eval batch, this is for chemical engineering. Okay, just see this. Outside it is very difficult to get the chemical engineering subjects coaching. Okay, you must thank to Unacademy. They provide a better facility to you. Utilize this facility. If any one of your friends are in chemical engineering, suggest them to join them. Already, this is the first batch. This batch is already started on 25th of January. Don't worry, even though it is a delay of 10 to 15 days, no problem, don't worry. Okay, the faculty will guide you. They cover the topics which were covered previously. They will cover the topics also. They will give a special schedule to you to cover those previous topics. Okay, don't worry. And there is a, for mechanical engineering, there is a eval batch for GATE 2022. This is also started from 25th of January. Here are the few top faculties who are going to handling the mechanical engineering subjects. And next, there is a Ascent batch for GATE 2023 for mechanical engineering. Here are the top educators from mechanical engineering. They are going to handling these subjects. This is going to start from 25th of January. Already started it is. So now we check what are the different disciplines available in Unacademy for GATE and engineering service. Mechanical engineering, electrical engineering, computer science and IT, CSC, civil engineering, production and industrial, instrumentation and chemical engineering. These are the different disciplines available. Now we check what are the different subscriptions available. Here there are two types of subscriptions available: plus subscription and iconic subscription. Okay, plus subscription and iconic subscription. In plus subscription, your classes are going to be taken care by the India's best educators, and there are interactive live classes, structured courses and PDFs. They will, and tests and quizzes. First of all, plus subscription is the basic plan to get you started. Okay, to get you started. And in iconic, it is the next level of the batch, and here personal coach is available. For every student, there is a personal coach. They will allot a personal coach to you. In addition to this, they will provide personal coach here in iconic batch. Okay, here India's best educators are available. So same interactive live classes, structured courses and PDFs, live tests and quizzes they will provide. And personal coach is the additional benefit here. And personalized test analysis also additional benefit here. Personalized test means analysis is once you've written exam, some test you attempted, okay, in that test they will check, they will analyze your paper from top to bottom, okay, and after that they note where you are strong and where you need more preparation, okay, where you are doing mistakes. They will write on a paper in a detail, and based on that they will prepare a proper study planner to you. Okay, and they will forward that one to you by following that study planner, and they will forward a proper study material to you. By following these things, all these things, definitely you get success in your life, in your career. Once success in career means success in life. Okay, so my dear students, don't waste your time. Whatever thing is happened, your learning process cannot be stopped. Okay, and if you observe the cost of this subscription and this subscription, okay, see, cost of this subscription for plus subscription cost is for 1 month this much you have to pay, for 3 months, for 6 months and for 1 year. Okay, so 1.5 years, 18 months and 24 months. Now after using my code VRAW10, after using my code VRAW10 during subscription, you get 10% discount. You get 10% discount. Okay, now If you check the cost of this, 27,225 rupees. This cost is hardly just more than the transport charge what you are spending for a year to attend the classes at outside. Okay, at outside, if you join somewhere for classes, okay, that cost of 27,225 rupees is whatever the additional expenditure you are spending on the for that coaching. That means transport. Okay, on the class day you need to take some breakfast, some lunch. For that, whatever the amount it takes, now that is more than that is this amount is just more than that, little bit amount. Now next is the iconic plan. This iconic plan is available for in two subscriptions. One is 12-month subscription, other one is a 24-month subscription. Okay, in 12-month subscription, after using my code VRAW10 during subscription, you get that one with a 10% discount, that is 45,225 rupees. Okay, so now this is the amount close to the amount what you are paying at outside, okay, institutions for taking the coaching. Okay, but here by paying this much amount, you may ask one thing, sir, the amount it is going to be equal to the amount what we are paying at outside. Okay, now how we benefited from this one compared to that? Here benefit is, the first benefit is, if India's top faculty are going to handling your classes. After that, once you've written exam, that your paper is going to be analyzed thoroughly. Okay, and where you are doing mistakes and where you are strong, they will analyze that, and based on that they will prepare a study plan to you. Okay, by following that study plan, they will, based on that test and your capability, okay, they will prepare the material also. For example, in some subjects, okay, your way of answering is not good, not proper, you are committing more mistakes. At that time, okay, they will concentrate more on that subject. That personal coaching is available. Personally, one coach is available to you. Okay, that coach is going to personally guide you. Okay, everything about you is going to be taken care by that coach. But in outside, it is very difficult to meet the faculty. Okay, hardly you may meet 5 minutes, you can talk freely with that faculty, because faculty is busy with taking the classes. Okay, and so many number of students, 100, 120, 180, like that strength is there. At that time it is difficult to spend the time with faculty to clarify our doubts. But here that is not the issue. And more important thing is, no need to move anywhere. By sitting at your home itself, you can get all these facilities. Okay, now we know today's situation at outside. We can't expect what is happening tomorrow. Okay, but whatever thing is happening at outside, our learning process cannot be stopped. That is the motive. Okay, so my dear students, please don't waste your time, enroll today itself and get maximum benefits. Now, today's session we are going to solving some of the important model problems on semiconductors. Okay, now we go on solve this problem. See this problem. First, the intrinsic carrier concentration of silicon sample, is at 300 Kelvin is 1.5 into 10 power 16 per meter cube. That means they given Ni value to you 1.5 into 10 power 16 per meter cube. After doping, the number of majority carriers is, so they given majority carrier concentration to you. So majority carriers equals to 5 into 10 power 20 per meter cube. After doping, majority carrier concentration is 5 into 10 power 20 per meter cube. So they want minority carrier concentration. Minority carrier concentration is how much? See, here I am going to using the mass action law. Mass action law. Mass action law. So we know that mass action law is at a constant temperature in any semiconductor. At constant temperature, the product of concentration of electrons and concentration of holes is equal to square of the intrinsic carrier concentration. Square of the intrinsic carrier concentration. Now, you can take any semiconductor in these two, one is going to be majority carrier, other one is going to be a minority carrier. For example, I am taking n-type semiconductor. In n-type semiconductor, electrons are majority, holes are minority. Now majority into minority equals to Ni square. So if you take p-type semiconductor, P is the majority carrier concentration and N is the minority carrier concentration. Now majority into minority is equals to Ni square. So that's I am going to be applying here. So majority carrier concentration into majority carrier concentration into minority carrier concentration. Minority carrier concentration is equals to Ni square. So now I am going to representing this majority carrier concentration. They given it is 5 into 10 power 20. Now minority we need to get. So therefore minority carrier concentration is Ni square by majority. So which is so I am representing majority by capital M, minority by small m. Now substitute values. Therefore minority is Ni square 1.5 into 10 power 16 into 1.5 into 10 power 16 by majority 5 into 10 power 20. 5 into 10 power 20. Just simplify this. Simplify this. Now this is 16, 16, 20. Now it is a 10 power 12. Now it is 5. It is in 0.3 times. It is a 0.45 into 10 power 12 per meter cube. So if you write, you can write this one is 4.5 into 10 power 11 per meter cube. This is the minority carrier concentration. Okay. Now just check this. Here is option 4.5 into 10 power 11 per meter cube. So this is the answer for this. Okay. So this is our first problem. I am going to move to next problem. See, silicon bar is doped with donor impurities Nd equals to 1.5 into 10 power 15 per atoms per centimeter cube. So they given it is a donor impurity. So Nd they given Nd is 1.5 into 10 power 15 per centimeter cube. Given the intrinsic carrier concentration of silicon at 300 Kelvin is Ni. Ni equals to 1.5 into 10 power 10 per centimeter cube. Assuming complete impurity ionization. The meaning of complete impurity ionization is whatever the impurity you are adding to that, all impurity atoms are going to replace silicon atoms. Once it is replacing silicon atom, it is going to provide it is donating one electron to you. That is the meaning of complete impurity ionization. By donating one electron, it became negative ion, positive ion. That is. Now the equilibrium electron and hole concentrations are, now they want under equilibrium electron concentration is how much and hole concentration is how much. See here, compared to compared to Ni, Nd is 10 power 5 times more. That means 1 lakh times more. So here now Nd is much greater than Ni. So once doping is much greater than Ni, amount of majority carriers. So it is a donor impurity they added. So this is N-type semiconductor. Okay, in N-type semiconductor, once this condition is present in that or exist in that, then you can write majority carrier concentration equals to amount of doping approximately, and minority carrier concentration is P naught, can be written as Ni square by Nd, because from mass action law we can write N naught into P naught equals to Ni square. Now N naught equals to Nd, so Nd value they given 1.5 into 10 power 15 per centimeter cube. Now we need P naught, which is Ni square by Ni value is 1.5 into 10 power 10 into 1.5 into 10 power 10 by Nd 1.5 into 10 power 15. Now this is 1.5, 1.5. Here 10 power 10, 10 power 10, it is 10 power 15. You get it as 10 power 5. So now it is 1.5 times 10 power 5 per centimeter cube. So electron concentration is 1.5 into 10 power 15 per centimeter cube, and hole concentration is 1.5 into 10 power 5 per centimeter cube. See, this is the option A. So N naught is 1.5 into 10 power 15 and P naught is 1.5 into 10 power 5 per centimeter cube. So I am moving to next problem. See, consider a silicon sample. Consider a silicon sample with Nd equals to 1.5 into 10 power 15 per centimeter cube donor atoms. So they given Nd value. Nd is 1 into 10 power 15 per centimeter cube. Assume that the intrinsic carrier concentration Ni equals to 1.5 into 10 power 10 per centimeter cube. So that means Ni is 1.5 into 10 power 10 per centimeter cube. If the sample is additionally doped with Na equals to 1 into 10 power 18 per centimeter cube acceptor atoms. So it is additionally doped with acceptor atoms. Na equals to 1 into 10 power 18 per centimeter cube acceptor atoms. The approximate number of electrons per centimeter cube in this sample at T equals to 300 Kelvin will be. So they want number of electrons. So approximate number of electron concentration is how much? So at the same time we calculate P also, hole concentration also. See here, this is composite doping because they are adding N-type impurity as well as P-type impurity. Na, Nd they are adding. And that too, by observing this data, Nd is 10 power 15 and Na is 10 power 18. So Na is greater than Nd. So here Na is greater than Nd. Okay, this type of case we studied at the time of charge neutrality. Okay, so once Na is greater than Nd, now the semiconductor behaves like P-type semiconductor. P-type semiconductor. Okay, so once it is a P-type semiconductor, hole concentration P is equals to Na minus Nd in the case if Na is much greater than Nd. Otherwise, you have to apply another formula. So later we check that one. Now Na minus Nd, that is the whole concentration. It is approximate value, sir. Now it is Na minus Nd is 1 into 10 power 18 minus 1 into 10 power 15. So now it is 10 power 15 take common. So it is 1000 minus 1, 999. So 999 is nothing but 1000 approximately. So you can take it approximately 10 power 18 per centimeter cube. So we got the whole concentration. Now electron concentration N is Ni square by whole concentration from mass action law. So Ni square value is 1.5 into 10 power 10 into 1.5 into 10 power 10 by P value. P value we got 10 power 18. So now it is 1.5 into 1.5, 2.25 into 10 power 10, it is 10 power 20, 10 power 20 by 10 power 18, it is 10 square per centimeter cube. Or you can write it as 225 number of electrons per centimeter cube. That is the electron concentration. So now it became 225 per centimeter cube and it is 10 power 18 per centimeter cube. Okay, so this is the problem. Now we move to next problem. So next one is an n-type silicon containing 10 power 15 phosphorus atoms. See, clearly they mention it is n-type. So it is n-type. And 10 power 15 phosphorus atoms they added. Okay, that means that is Nd. Nd is 10 power 15 phosphorus atoms. Donor impurity concentration is 10 power 15 per centimeter cube. Is doped additionally with 10 power 17 boron atoms. Now this n-type is additionally doped with 10 power 17 boron atoms. Boron atoms is nothing but a acceptor impurity. It is doped with 10 power 17 boron atoms per centimeter cube. Calculate the electron concentration in this semiconductor. See, here also it is also a composite doping. Now Nd 10 power 15, Na 10 power 17. So Na is greater than Nd. So it is a p-type semiconductor. Once it is a p-type semiconductor, whole concentration is approximately Na minus Nd. Because compared to this, it is 100 times more Na is. So after simplification, you get it as approximate value 10 power 17. So 10 power 99 into 10 power 15 you get. So that is close to 10 power 17 per centimeter cube. And the electron concentration is as it is Ni square by P. So we know Ni square value 1.5 into 1.5 into 10 power 10 into 10 power 10. This is Ni square by P value. P value is 10 power 17. 10 power 17. Just simplify this. Now it is 2.25 into 10 power 10 into 10 power 10. 10 power 20 by 10 power 17. It is 10 power 3 per centimeter. So both are similar problems. Okay. Now I am moving to next problem. See. So this is a good problem. Silicon atoms at a concentration of 10 power 10 per centimeter cube. Silicon atoms at a concentration of 10 power 10 per centimeter cube. That means silicon concentration is 10 power 10 per centimeter cube are added to gallium arsenide. This is added to added to gallium arsenide. Assume that the silicon atoms are fully ionized. Sir, you observed or not? So far, whatever the problems we studied, in that the impurity atoms are completely ionized. That is the statement they mention. But in this case, they mention silicon atoms are fully ionized. That means your silicon is going to be acting as a impurity to gallium arsenide. Now, see, and in that 5% replace gallium atoms. In this 10 power 10, 5% replace the gallium atoms. So 5% of silicon atoms replace the gallium atoms, 5%. Next, and 95% replace arsenide atoms. Now these silicon atoms are going to replace 95% of arsenide atoms. 95%. Okay. Take the temperature to be 300 Kelvin. Calculate the electron concentration in per centimeter cube. Take Ni for gallium arsenide is 1.8 into 10 power 6 per centimeter cube. Now, this is the data. Now, from this data, what we can understand, we check it. See, here silicon is adding to gallium. Silicon is the impurity. Now here gallium arsenide is, by combining gallium arsenide, it is taken as a, now here it is acting as a semiconductor. It is the semiconductor. Now here it is acting as a impurity. Silicon acting as a impurity or doping. Once you are adding impurity to that, few of the semiconductor atoms are replaced by silicon, replaced by impurity atoms. That is the procedure. Okay, now here also gallium atoms are replaced by silicon atoms, as well as arsenide atoms also replaced by silicon atoms. Okay, now if you check the gallium is the third group material and arsenide is the fifth group material and silicon is fourth group. See, 4 plus 3, 7. Okay, that means for getting stability 8 electrons required. Now 1 electron is lagging, that means 1 hole is available. So with respect to gallium, silicon acting as a acceptor. Therefore Na is acceptor, impurity is 5% of silicon. So 5% of silicon concentration. So that is 5% means 0.05 into silicon concentration, they given 10 power 10 per centimeter cube. So far I got the Na. Now in this case, with respect to arsenide, silicon acting as a donor, because 4 plus 5 is 9, 1 excess electron is there. It is donating 1 excess electron to you after adding silicon to this. Now Nd is 95% of silicon concentration. That is 0.95% means 0.95 into 10 power 10 per centimeter cube. Okay, so this is nothing but, now Na is there, Nd is there. Now it is a composite doping. Now therefore, and in this if you observe, Nd is much greater than Na. So this is a N-type semiconductor. Once it is n-type semiconductor, electron concentration N equals to Nd minus Na. See, that too, this is not that much greater compared to this. It is 10 power 10, it is 10 power 10. 10 power 10, 10 power 10, not that much greater. It is lightly doped one. So, in that case, there is an equation for electron concentration. That equation is, now Nd electron concentration is Nd minus Na by 2 plus square root of Nd minus Na by 2 whole square plus Ni square. This is the equation for electron concentration. Okay. Now, I am going to simplify in this. Nd minus Na by 2. So, Nd minus Na by 2. First I am taking Nd minus Na. 0.95 minus 0.05, it is 0.9 into 10 power 10 per centimeter cube. So, it is 0.9 into 10 power 10 power 10 by 2 plus square root of, this is 0.9 into 10 power 10 by 2 whole square plus Ni square. The given Ni value is 1.8 into 10 power 6. 1.8 into 10 power 6 whole square. Okay. Now this one is, just simplify this. This is 0.45 into 10 power 10 plus square root of 0.45 into 10 power 10 whole square. So now it is, now I want 0.45 into 0.45. So 0.45 into 0.45 is 0.2025. 0.2025 into 10 power 20 plus 1.8 into 1.8. 1.8 into 1.8, that is 3.24 into 10 power 12. See, here you observed or not, compared to, now okay, this is compared to this 10 power 20, this 10 power 12 is small value. Okay, so you can neglect that value, or if you are considering that one, it is not much variation. Now we can neglect this one. By neglecting this one, you get, this is also 0.45 into 10 power 10. So finally you get 0.9 into 10 power 10 per centimeter cube. So this is nothing but a 9 into 10 power 9 per centimeter cube. It is approximately Nd minus Na. That is. Okay. Now go and check the options. We got 9 into 10 power 9. Yeah, here 9 into 10 power 9 is there. 9 into 10 power 9. The option. Okay. So this is important, sir. Okay, here the single semiconductor silicon is acting as a doped impurity to gallium arsenide. Previous problems we added gallium as the impurity to silicon or arsenide as impurity to the silicon, but in this case it is different. Okay, so this is a nice problem. So now I am moving to the next one. See, silicon is doped with boron atoms, doped with boron to a concentration of 4 into 10 power 17 atoms per centimeter cube. So doped with boron means it is Na. Na is 4 into 10 power 17 atoms per centimeter cube. Assume the Ni of silicon to be 1.5 into 10 power 10 per centimeter cube. And the given value of Kt by Q also. Kt by Q is 25 millivolts. So from this you can write Kt is 25 milli electron volts. Okay, 25 milli electron volts at 300 Kelvin. Now they want compare to undoped silicon. The Fermi level of doped silicon. Sir, undoped silicon is nothing but a intrinsic semiconductor. Intrinsic semiconductor. So compared to undoped silicon means intrinsic semiconductor Fermi energy level minus Fermi energy level of doped silicon. Now this is a p-type semiconductor. Now the Fermi energy level of p-type semiconductor is EFP. Is how much? Already we derived the equation for this. So from that the value of this one is so EFI minus EFP equals to KT into ln of whole concentration by intrinsic carrier concentration. So now this Na is nothing but a whole concentration under thermal equilibrium. Okay, approximate value it is. Because compared to Ni it is 10 power 7 times more. Forget about this constant, it is not that much impact. 10 power is the impact one. So compared to this it is 10 power 7 times more. That means 100 lakhs more. Now I am substituting these values. P0 we know and Ni we know. And Kt also 25 milli electron volts. So that is 25 milli 0.025 electron volts into ln of P0 4 into 10 power 17 by Ni 1.5 into 10 power 10. Just simplify this 0.025 into 4 by 1.5 4 by 1.5 it is a 2.66. So ln of 2.66 into 10 power 7. Now it is 0.025 into ln of 2.66 plus 7 into ln of 10. Ln of 10 we know that it is a 2.302 something. So it is 0.025 into ln of 2.66. So ln of 2.66 it is 0.978. 0.978 plus 7 into ln of 10 is 2.3. So it is 7 into 2.3 16.1 plus 0.978 it is 17.0 into 0.025. So it is 0.426 electron volts. So EFI minus EFP is 0.426 electron volts. So now check the options. Here 426 or 427. and that too it is goes down compared to, in a P, it is a p-type semiconductor. Now Fermi energy level is less than the Fermi energy level of intrinsic semiconductor. Okay, so that is important, and from this you should be in a position to represent the relation between any energy levels of a semiconductor. See, now let us take, this is EC and it is EV. We know that the energy gap of this one is 1.1 electron volt at 300 Kelvin. Now I am going to representing intrinsic Fermi energy level EFI. It is approximately midpoint of that EFI. So EFI here in this sense, this is going to be 0.55 electron volt, half of this. Similarly, this is also 0.55 electron volts. And after that, your Fermi energy level, just before we get EFI minus EFP is 0.426 electron volts. 426 electron volts. So EFI minus EFP, EFI minus EFP. So it is somewhere here, EFP, Fermi energy level of p-type semiconductor. EFP, it is 0.426 electron volts. Now here I am going to representing with respect to EC how much for Fermi energy level, and with respect to EV how much for it is. Now it is a plus 0.55 I am adding, that is 0.976. This one is 0.976 electron volts, and this one is, just subtract from 0.55 minus 0.426, that is 0.124, 0.124 electron volts, 124 electron volts, this one. And similarly this one we got, this is 0.976 electron volts. Now see this, with respect to valency band, Fermi energy level of the doped semiconductor is 0.124 electron volts above the valency band and 0.976 electron volts below the conduction band energy level EC. Okay, like that. Once you know the one relation, once you get from this diagram, by using the approximate value of 1.1 electron volt energy gap and Fermi energy level is midpoint of that energy gap, by using these 2 points you can estimate the position of Fermi energy level of a doped semiconductor with respect to any energy level. Okay, so be practice this, there is a chance of getting this type of question. Now see, an n-type silicon wafer, clearly they mention it is n-type, has been uniformly doped with 10 power 15 phosphorus atoms. That means Nd they given 10 power 15 per centimeter cube. Calculate the position of Fermi energy level with respect to intrinsic Fermi energy level. So with respect to EFI, what is the position of Fermi energy level? And use Ni, they given Ni 10 power 10 per centimeter cube. That's it. Okay. See, for n-type semiconductor, we need to relate the Fermi energy level of n-type with Fermi energy level of intrinsic semiconductor. We have an equation for that. That equation is, already we derived that. That equation is EFN, because Fermi energy level of n-type p-type n-type semiconductor is more than the intrinsic Fermi energy level. EFN minus EFI equals to KT into ln of N0 by electron concentration N0 by intrinsic carrier concentration Ni. Okay, and at room temperature they given, so you can use KT value is 25 milli electron volts. Just to substitute the value, so it is 25 milli, 0.025 into ln of N0 is nothing but your Nd, because compared to Ni, Nd is 10 power 5 times more, 1 lakh times more. So you can take majority carrier concentration is approximately amount of doping. So it is 10 power 15 by Ni value is 10 power 10. So now it is 0.025 into ln of 10 power 15 by 10 power 10. That is nothing but a ln of 10 power 5. So now it is 0.025 into, so ln of 10 power 5 is 5 into ln of 10. Ln of 10 is 2.3. So now just simplify that. 0.025 into 5 into 2.3. That is 0.287 electron volts. 0.287 electron volts. Now I want, this is the EFN minus EFI, but now my new question is, what is the value of, now my question is, what is the value of Fermi energy level with respect to conduction band? What is EC minus EFN? How much it is? Okay, and the second one is, what is EFN minus EV with respect to valency band? What is this position? Now for that, just you need to go for its energy band diagram, complete energy band diagram. Okay, this is the equation for EFN minus EFI. Okay, now I am going to complete energy band diagram. See this? EC, EV, and taking EFI at midpoint of this approximately. Okay, and they given Fermi energy level EFN above the EFI, above the EFI, this one. Now this is EC and it is EV, it is EFI, intrinsic Fermi energy level, and it is EFN, n-type Fermi energy level. So we know that from here to here it is 0.55 electron volts. Similarly here to here also 0.55 electron volts, 0.55 electron volts. And from problem, EFN minus EFI, EFN minus EFI is 0.287. This is 0.287 electron volts. Okay, and now this is the Fermi energy level. Now with respect to EC means I want this value. This is equal to 0.55 minus 0.287, and at the same time I want this one with respect to EV. That means it is 0.55 plus 0.287. So plus 0.55, it is 0.8375. Now this value is 0.8375 electron volts. Sorry, and this one is 0.2625, 0.2625 electron volts. Okay, so this is the complete energy band diagram. So this is your complete energy band diagram. So like this, you can write the complete energy band diagram based on the information. Now I am moving to next problem. See, Fermi level in a silicon sample at equilibrium is located 0.4 electron volts below the middle of band gap at 300 Kelvin. See, EC, EV, it is EFI. Now, Fermi energy level is located 0.4 electron volts below the 0.4 electron volts below the Fermi energy level. Somewhere here, it is 0.4 electron volts. It is the Fermi energy level they given. So, determine the probability of occupancy of a state located at the middle of the band gap. So you need to measure, determine the probability of occupancy of a state, energy state or energy level located at middle of the band gap at this point. See, probability of occupancy. So probability of occupancy is F of EC. We know that. Okay. In F of EC, we are studying probability of occupancy. F of EV also you can write probability of occupancy. But probability of vacancy is 1 minus probability of occupancy, EV or EC. Now, to generalize this equation, what I am doing is, whatever the subscripts here I have, I am going to removing this. Okay, so now probability of occupancy is F of E and probability of vacancy is 1 minus F of E. Probability of vacancy is 1 minus F of E. So in this problem, they want probability occupancy of state located at middle of the band gap. So state located at middle of the band gap is EFI. That means at E is equals to EFI they want. Okay. So the equation for F of E we know that, which is 1 by 1 plus E power E minus EF by KT. This is the equation for probability of occupancy. Okay. Now, they given E is equals to EFI. At E is equals to EFI they want. Therefore, F of EFI equals to 1 by 1 plus E power E means EFI minus EF by KT. Now, which is equals to 1 by 1 plus E power EFI minus EF. EFI minus EF, they given it as 0.4 by KT value. So you can take KT value is 25 milli electron volts. As usual, KT is 25 milli electron volts. Okay, 25 milli, that means 0.025 milli electron volts. Okay, now that is divided by 25. It is 16 e power 16. So that is 1 by 1 plus e power 16. Which is 1 by 1 plus e power 16. So that is this much. This is the probability of occupancy. Just simplify that. We have another part in the problem, that is determine the probability of occupancy of acceptor states if they are located 0.5 electron volts above the top of the valency band. Now the same procedure, sir. Now this is acceptor energy level is 0.4 electron volts above the valency band. Again, but they want occupancy. Now they are saying EC, EV. So Fermi energy level is 0.4 electron volts above the valency band. 0.4 volts above the valency band. Okay, at that time they want to calculate the Fermi energy level of acceptor Fermi energy level. See this. Determine the probability of occupancy of acceptor states if they are located 0.4 electron volts above the top of the valency band. Acceptor energy states occupied, sir. Acceptor energy states. They did not mention it is a Fermi. Acceptor energy states. That means it is EA. It is going to be EA, acceptor state. 0.4 electron volts above the EV. Okay. So once it is 0.4 electron volts above the EV, now they given basically it is a silicon semiconductor. Okay. So acceptor energy level is 0.4 electron volts above this. This is EFI with respect to Fermi energy level where it is located. So we know that this is 0.55 electron volts. Now it is 0.4 they given. Now it became 0.55 minus 0.4. It is 0.15 electron volts. Okay, now I want the probability of occupancy at this level. So I want at E is equals to EA. Now the equation is basic equation f of E equals to 1 by 1 plus e power E minus EF by KT. Okay, now I am taking at E is equals to EA. So f of EA equals to 1 by 1 plus e power EA minus EF by KT. So EA minus EF is 0.1 minus 0.15. So it is 1 by 1 plus e power minus 0.15 by KT, 0.025 electron volts. Just to simplify that, you get the probability of occupancy at acceptor energy level above 0.4 electron volts of EV. Okay, so these are the problems, and next session we continue the remaining problems. Okay, so thanks for your spending your valuable time with us, and please don't forget to use my code during subscription VROW10, and by using this code you get 10% discount, and hit the bell icon to get the notifications, and join our Telegram group to get the latest updates and upcoming videos, and please give your valuable suggestions or comments on YouTube, okay, to strengthen ourselves and to provide a good quality information to the upcoming students. Okay, don't forget to subscribe. Thank you very much. Thanks to one and all.